Welcome back. Time for another energy risk engineering lesson. Glad you could make it. If you don't know who I am, I'm John Muno. I'm an energy risk engineer, and I've been in the industry for several decades, and I make videos about energy risk engineering that can benefit underwriters, risk engineers, mechanical and civil and electrical engineers who want to get into risk engineering, as well as owners of all this energy equipment that can sometimes fail and sometimes catch on fire. Today's lesson will be on battery energy storage systems, and we're going to talk about large losses that have occurred over the last several years, about $1.5 billion. We'll talk about some common themes and some ways that we can address what's going on. There's a battery energy storage system failure. Didn't take much to figure that one out. But you can see that the smoke's propagating towards the transformer, that in this case, the heat and all is at one end. It doesn't look like it's involving the unit on the left, but it could involve the other units, and we just have to wait to see. You can see that there is some charring on the adjacent units across the aisle, and I see some smoke coming off of the item, off the machine at the bottom of the screen, at the module at the bottom of the screen. We'll talk about this. How do we stop this propagation, and what are some of the lessons that we've learned from all these big fires? And why does it matter that we need to worry about these big fires? Because there's a BESS boom. And this boom has gone from 5 gigawatts back in 2020 to almost 55 gigawatts in 2025, more than tenfold in just a few years. And with the BESS growth, we're seeing fires. And the more fires we see, we're going to attract more attention from underwriters and regulators and the public. And we want to get ahead of that, manage it, and make sure that it's a safe industry. We're looking at over 50 major fires in this time period. My information here has come from internet research and from AI help. And what I'm going to cover is just a handful of these 50 major fires. Looking at over $1.5 billion in property and downtime and cleanup. And remember that the downtime is going to be affected by the cleanup. If cleanup is so complicated that it takes a while, then that's going to shut you down for a while as well. Human toll, we've got deaths to people, we've got injuries to people. So we want to stop all that. And certainly there have been deaths involving e-bikes and electric vehicles. What I'm going to focus on today is BESS systems, fixed battery energy storage systems, where they're more of a utility type exposure versus an apartment building or a hotel or somewhere where you're going to have a lot of people and just one little battery that ends up hurting everybody. There's a boom. Fire's coming with it. All right. Where is it happening? In North America, we can look at some of the names, and some of them are familiar. We'll go through, but you can see over $300 million in cleanup equipment losses and environmental remediations in North America. So it's significant. We'll talk about Moss Landing. That's the one that everybody could probably identify if it was a Jeopardy question. Name one battery energy storage system fire, Moss Landing. And it happened in 2025, this year. There were some lessons learned, and I might say that it happened twice. It happened in January and it happened in February because it reignited. And what happened at Vistra's facility, about a 300 megawatt facility, it was the world's largest, and the fire originated in the oldest battery array that was installed back in 2020. The flames spread rapidly. They destroyed most of the batteries in one building. And like I said, a month later, it reignited. They investigated it, and they couldn't really determine a trigger, but they think that there were cell defects or overheating that was exacerbated by how dense these batteries were packed in together. And they had no effective propagation barriers, nothing to really stop it from going from one module to another. The clean agent system that they used did not cool the cells. All that it did was extinguish the flame. Again, a Halon or a FM200 or a Novex system, they're going to attack a fire by getting involved with the chemical reaction between the fuel and the oxygen. And the way they do that is they consume the oxygen. It's a material that actually burns, but not with enough exothermic heat to continue the chain reaction that's going. So effectively, you're removing oxygen from it and you're not adding heat back into it. So this interferes with that chain reaction. It keeps a typical flammable liquid fire from burning, but it just doesn't work for battery cells. If there's any manufacturers of these clean agent systems that would like to correct me or challenge that statement, please say so in the comments, and I'd love to have you on and we'll talk about it. All right, losses at Moss Landing were about 100 million in damages, and we had about 1,000 people that had to be evacuated. There were road closures, complaints of headaches and nosebleeds. Soil and water testing showed that we had elevated levels above EPA requirements. We had potential for carcinogenic activity. And then there's a lawsuit against Vistra in the end for inadequate safety. After the incident, the California Public Utility Commission made a rule and required real-time monitoring. Okay, it's hard to believe that at the beginning of 2025, we didn't have a requirement for real-time monitoring, and it could just be an alarm that there was smoke or a fire. That's not the same thing as knowing what the cell voltages are and the currents and the state of charge. Now that's required, at least in California. Independent soil analysis also confirmed contamination. The idea of integrating toxic gas monitoring was well-intentioned. I believe that by the time you're making enough gas to be monitored, that you're already into thermal runaway that takes away your ability to stop the fire. It's going to happen, and it's just a matter of how much fuel you're going to let it have before it stops making toxic gases, unless you stop the thermal runaway. And we'll talk about how you do that with another fixed system that we have coming along this year. Next event was Moorabool in the Victorian big rig battery in Australia back in 2021. And during commissioning, 2 Tesla megapacks ignited, fire propagated to an adjacent unit. A coolant leak caused a short circuit, and that led to the thermal runaway. And then their alarm system basically locked in an alarm, and they weren't aware of everything else that was happening. They needed to improve the alarm prioritization on the system. And they overlooked the risk of a leak of the coolant system when they were installing it. You can't just do a pressure test on liquid piping and assume that means it's not going to leak. You need to do a flowing test. Once you do a flowing test, you take into account velocity pressure and water hammer effects, so that if you shut down the flow of a liquid in a pipe quickly, for every foot per second that liquid was traveling, you've just created 10 psi of pressure from that velocity pressure turning into static pressure. And if you're moving 50 feet per second, you're talking about 500 psi. Your systems aren't going to be made for that high pressure, and you're not going to know what it's exposed to unless you do a flowing pressure test where you're actually running the coolant and making sure that you can operate it before you put the batteries in. The losses were 50 million in damages and delays, and don't forget that the entire project had to be postponed to be connected to the grid. Again, this was only a couple of arrays that burned up, but the whole site was impacted. So again, if we can figure out a way to limit the damage and limit the effects to as little equipment as possible, then we can get our sites back up and running as quickly as possible. There was an environmental release of hydrogen fluoride, very caustic to glass, to your lungs, not something that you should breathe. After the incident, Tesla updated their firmware and fixed that battery module isolation loss alarm. They mandated pre-site coolant inspections. They disassembled the cell, and they figured out that it was conduction from cell shell to cell shell. The lessons learned were to validate these cooling systems and use layered alarms in the BMS. Beijing, China, April 2021, had an explosion in a commercial battery energy storage system, and this one actually led to some fatalities. It's something that we want to pay attention to because we don't want it to happen. We don't want anybody getting hurt or killed for responding to fires on equipment like this. But again, cascading thermal runaway from overcharge or short circuit, poor ventilation led to gas buildup, hydrogen, carbon monoxide. Remember, carbon monoxide is not carbon dioxide. Carbon dioxide can be used to extinguish a fire, not a lithium-ion battery fire by itself, unless you have dry ice and liquid nitrogen in a slurry. And then you've got the ELSA Carver fire protection system that we can talk about more towards the end and sometimes throughout the presentation. But carbon monoxide is explosive, and it's combustible, and it's poisonous. Hydrogen, it's explosive, it's an asphyxiant, not necessarily a poisonous agent, but both of them, we want to be careful about how we vent them and how we let them interact with oxygen. They had inadequate emergency procedures. They just thought they could do the same thing as they would for a bus fire out on the street or a house fire or any room that had a fire in it. They think they just open the door and spray water. They're finding out that's not the thing to do with battery fires, battery energy storage system fires. 20 million in damages, a couple firefighter fatalities, and multiple injuries. After the incident, the hazard mitigation analysis revealed no barriers to stop the propagation, and that the suppression was ineffective and inefficient. Again, like I said, you can't just open the door and spray water because your water's not getting to the actual place where the thermal runaway is occurring. There's not enough heat capacity in it. It boils away and turns to steam. Steam doesn't conduct heat the way water does. As you're converting your water to steam, spraying it on this hot metal, you're losing your water. Whereas some of this other concept of dry ice and liquid nitrogen, you'll boil some of that liquid nitrogen, but that dry ice is going to cool. Because it's hard and it's a solid, it's going to take a lot more energy to turn it into a liquid or make it non-conductive. That's the beauty of this solution. The other thing we want to do is we want to train the responders on deflagration risks. They are probably used to black fires, to oil fires, or fires involving furniture in a house which have black smoke. They're used to the backdraft potential from those type of fires. And if they go into a battery energy storage system fire and see white smoke, they're probably not going to realize they have a backdraft potential. We need to improve training and make sure that they don't open the doors of these modules, except maybe with robots. And there are robots that handle battery fires. They do it all the time at Fire Rover. Fortunately, they're just typically little battery packs, little batteries in a large pile of garbage at a waste processing facility. But they handle and they extinguish hundreds of lithium-ion battery fires a year with robots. Yeah, they're not BESS battery energy storage system modules. These are just little battery packs. Chandler, Arizona, back in 2022, a containerized fire. It burned for over 10 days, and they say it required continuous sprinkler cooling. All right, let me say that either they sprayed water on it for 10 days because it wasn't very effective, or as they sprayed it for 10 days, they were able to see some impact on the spread of the fire. In either case, the whole idea of spraying water for 10 days, it's going to bring in the media. A small fire that's out in an hour, the media may not even show up. But if you have a fire that's going on for 10 days, they're going to show up and their coverage is just going to get worse and worse. So we want to get these things over with as quickly as possible and hopefully get away from just spraying water on them for days and days, creating runoff and having to deal with that. They believe it was likely due to a manufacturing defect that triggered thermal runaway again, and that it propagated because of tight module spacing. This is a common theme. That's why we're hearing it over and over. The losses, they impacted, there's about 30 million in property loss, no major injuries, but it was a prolonged response and it strained resources. So again, the firefighters that would have been out handling other fires in the community were all dedicated to this fire. They backfill in their stations from surrounding communities and everybody feels an impact. And eventually your fire goes out and everybody can go back to their normal firehouses. After the incident, they determined that UL-style testing showed that the water-based suppression was effective for cooling, but it did risk creating more shorts that could start more fires. So we have to be careful about what we're doing by putting water onto a burning battery. Having doors being opened either remotely or with robots is a new lesson. That's something that we want to do. We don't want people to open them at all. We want to be careful that we may not have to open them at all if there's a suppression system already operating. The lessons that we learned is we have to design for long duration fires. That's true if all we're doing is spraying water on them and waiting for them to burn out. That's true if let it burn is the philosophy. If we start to adopt some of these new approaches with the dry ice liquid nitrogen slurries, then we may be able to extinguish these fires very quickly and not have to worry about long duration fires anymore. And we want to incorporate some sort of secondary containment for runoff if we're using water. If we're using dry ice liquid nitrogen, we don't really need to worry about runoff. If you're using another clean agent, you're not going to put the fire out at all. You're just shutting down the flames, but the thermal runaway is going to continue. So then they're going to cool everything down with water, so you need water containment to capture all the runoff. Let's go to South Korea. South Korea, we've got events from over a 3-year period, over 27 fires and multiple events, some destroying buildings, poor installation, dust, humidity, and some didn't have good short circuit protection. Some have substandard monitoring. I've talked about monitoring again, where you can have remote monitoring that involves AI on site looking at all your equipment, or upload all your SCADA data to the cloud and then have AI interpret it. But with good monitoring, these vendors are telling me they can detect thermal runaway days to weeks to months before a gas detector or a smoke detector is going to detect it. Look at some of the other videos on the channel and get some more information about the different products that are out there for remote monitoring. What happened? Over 200 million in losses cumulative. Some of them were building losses. Again, the responders were unaware of the risks, and now we want to make them very aware that we don't need you entering into these battery modules to control the fire. Government probes emphasize controls, and they want integrated BMS. Points out that lithium iron phosphate batteries can burn. I've had discussions with insurers. I've tried to argue that they don't, and they said yes, they do. And there's some examples out here now that they do. We have to treat them the same way. We might feel more comfortable and the frequency of fire might be lower, but in the end, fire protection is not really based on frequency. It's based on how to stop the consequences. And once we know these consequences are possible, then we don't want to have a cascading lithium iron phosphate battery fire either. One of the things that we want to do is have site-specific hazard mitigation analysis, and we want to share our failure data internationally. Now, here's what everybody wanted to hear about in the first place: the common themes and the root causes. Thermal runaway is the common theme. Thermal runaway is the common theme. And what are the triggers to thermal runaway? 60% are from defects and overcharging. 30% are from abuse, like leaking water getting on them. And 10% are from dust and temperature swings. Again, this is internet data, internet information. Propagation modes. How does the fire propagate once the thermal runaway starts? Heat conduction. Heat can transfer through conduction, convection, and radiation. And in these cases, it was conduction from the cell shells to the other cell shells. We can also release gases that are explosive or combustible. Hydrogen fluoride, each one of those constituents. Carbon monoxide that I mentioned earlier, again, it's explosive and combustible. The failures of the mitigation efforts, the clean agents just will not cool the batteries. It will stop the flame, and then that will stop some of the radiation heat that's going back to the module system to cause it to burn more intensely. So it might appear that you're adding some control, and it's slowing down the rate of burn a little bit. But without barriers, even with clean agents, you're going to have a cascade. We need to figure out some way to stop the cascade or put in barriers. Response gaps and the barriers can be spacing or material, physical. Delayed detection. Again, here we go. What are we trying to detect? If you're just trying to detect the heat of the battery, that's going to take a while. If you're trying to detect smoke coming off, that's going to take even longer. But if you're up front detecting some of the electrical signature of what the battery current is doing, you can learn a lot about the battery health and what's about to happen before it actually fails and gets warm, or gets warm and makes smoke. We want to be careful about what we're trying to detect and how we're monitoring our systems. And then another gap is that unsafe entry is what leads to injuries. Don't do it. Systemic issues, we're looking at rapid scaling is outpacing our standards. We just had a release of some NFPA guidance, some Canadian guidance, and I'll say that it's all trying to keep up with the information that's out there. I see the fire report one day, I write an article the next day, And a few weeks later, somebody who saw me on LinkedIn wants to talk to me about something they make that can stop thermal runaway. And it's not in the standards. It's not something that industry is practicing yet. I'm trying to get those words out to everybody through LinkedIn, through my YouTube, through Spotify, and through conferences. All right. What are the lessons learned? Prevention and the overreaction. The battery system has to monitor down at the cell level. We can't just think about the battery casing and figure that we're going to wait until the whole casing gets warm. We have to isolate anomalies at the cell level early. Look at Moorabool's alarm update that prevented repeats. We didn't have the alarms coming in over and over, so the attention to the incident wanes. Once, they're doing their thing, they got this one alarm, they don't know what it's for, other than there's a general battery monitoring system alarm. Whereas if they had all the other sub-alarms coming in with it, that would have helped. Layered alarms would have really helped. And not having just a single line of defense, but combining detection, venting, cooling, and water risks shorts. But in Chandler, they say it excels in cooling and prolonged events. That's an oxymoron to say it excels it, but yet it was prolonged. Just be the judge as to how you think that water is helping. Forensic protocols, make sure that we save everything to learn as much as we can. Use drones to heat map, but don't count on drones seeing a fire. Drones flying over a BESS facility are not going to pick up the type of fire that we want to as fast. We're going to want to pick it up before it goes into making smoke and before it goes into making flames. So drones are great during the event and doing IR heat maps when you're trying to respond, but let's just not rely on them as a way to detect an incipient battery failure. The Beijing analysis told us that we had to have good venting. Want to be careful about whether we're venting vertically or venting to the sides and think it through. If we're venting vertically, is in an area where snow will block the vents. If we're venting on the side, will it extend across the aisle to the next modules? We have to look at venting as an entire engineering discipline of itself. Then emergency response plans. They have to address deflagrations. People have to realize that just because it's white smoke doesn't mean that it won't erupt into a fireball. And then use robots for high-risk activities like opening the doors. Another lesson learned, just let's try and get our data shared out to the EPRI database. And that way more people can learn from the lesson of the bad experience or the misfortune that anybody has. And then the chemistry nuances. Don't forget that we have seen lithium iron phosphate be involved in these fires. And it's not the be-all, end-all. It can help, but we have to be prepared that it won't. We have to test all configurations. And then health focus. We want to monitor the toxics. We want to have secondary containment for runoff. But again, we want to, as much as we can, shut it down, cool it down, make the toxics stop, and not do it with a product like water that's going to cause runoff. We'll talk about some of the other ways to do it. The ELSA system, which is by Carver Fire Protection, and they're online on the internet. You can watch videos of them actually extinguishing an electric vehicle battery pack, not an EV car, but the actual battery module itself. They started in thermal runaway with heat, and then after it's burning really good and hot and sparking and shooting smoke and everything everywhere, they turn on this ELSA, and the fire goes out very quickly, just minutes, and then they can't reignite it. By the way, that's how when you test a battery pack, how do you dispose of it when you're finished doing your tests? You light it on fire again and you burn it up. They couldn't light this one back on fire. And this isn't the one that they put out with the ELSA, but I'm just showing you that this is a concept of what it would look like if they needed to either attack it remotely, but they can even pipe this up to where it's fixed, and you can have one of these systems on the right manifolded into several battery energy storage modules, and all of them zoned so that the right one gets the protection. This is the solution to removing the heat leg of the triangle, and I'm happy to talk to anybody about it, happy to put you in contact with the company, and just excited to see all the new technology that's coming out in response to all the fires that we've been having. With that, let me say thank you, and check me out on YouTube. I'm down at Energy Risk Engineering, LinkedIn. and Spotify. I do podcasts on Spotify that are really nice. They're very polished. They're all about energy risk engineering topics. They're created with the Notebook LM, if you've ever dove into some of those AI projects. And then again, on LinkedIn, I have many white papers and articles that I've published, and you can download the ones that you'd like to keep and share the ones that you think everybody benefit from. With that, share and subscribe this video, and I'll see you on the next one. Thanks again.